All right, so let's get started. So let's start from a couple of Q&A last time. Oh, one more thing to let you know. At the last 20 minutes of today's course, we will announce our first assignment. And I'll hand over to a TA to briefly go through what you are going to do and what is our expectation on the first assignment. Okay. So the first QA is, does HPD controller always map anti-parallel and parallel magnetic directions to be 0 and 1, and can it change? The answer is yes. Actually, like it is controlled by the firmware. So if you are going to map anti-parallel to 1 and parallel to 0, it is possible. And not only HDD controller, it if like SSD or like DRAM, they also has this kind of mapping stuff. Like for SSD, we say maybe high voltage and low voltage. Should it be 0 or 1? They can be changed in a firmware. Okay, so this can be changed, but not online. I mean, just like once before the boot, we need to decide what is the mapping between the bit and the physics stuff. Okay. And the second question is, does the SMR drive have lower random write performance compared with the conventional CMR drive? And the answer is probably yes, but actually it depends, because usually we even there is a remodified write phenomenon like we need to do in SMR drive out there, but actually in practical systems, SMR drive, they will maintain a log area. What is a log area is maybe they will maintain an area for logging the write update. So actually, when there is a write request coming, the write data will be first put in the log area instead of directly doing a remodified write. So actually, in like practical SMR drive, there's no very obvious random write performance drop every time. But the thing is, this is for a normal case because we have large enough of the log area. So if one day there is no sufficient space for the log area, then the SMR drives needs to do the carbon collection, and this will hurt the performance. So this is why, like, in the long term, like there will be some timing the SMR drive will face the like performance drop because it is doing the GC. Okay. So there is a third one is in a real system, requests arrive dynamically. How does SSTL handle newly arriving requests? Oh, SSTL is the shortest seek time first scheduling. So I think the question is about how can we know what is the shortest seek time? So actually in the systems, I mean the operating systems, there is a request buffer. So when the request keeps coming, the request buffer can absorb and hold those requests. So there is some time for the operating system to do this kind of, you can say it is more like we will first screen through all the received requests so we can do this kind of decision. And the reason is because usually this handling this request is time consuming. So request coming is super fast, right? Because request is using networking, and then it usually has a good amount of requests coming to the system. So actually, like the hard disk drive cannot handle that fast. So we need a request buffer to buffer those coming requests. Otherwise, the quick request will drop. Okay. And I think this is the last one. Like in Red 5, parity checks can be used to recover data chunks after disk failure. And can parity checks be used to detect errors? This is a very tricky question. I would say it depends on how to detect errors. Because if you are talking about to detect like 1 bit or 2 bits, then it is not possible. Because if you still remember the parity chunk, it is a chunk, so usually it is like 512 byte area or even a larger. So what parity chunk can really check is about if there are some arrows in a chunk. So it can only tell us the chunk as like there is some arrow in the chunk, but it cannot know where is the arrow. We can only know that arrow. Sorry, we can only know that chunk gets arrows. This is a little bit different against the error correcting code. The error correcting code, people call it BCC. There's also using some mathematical way like LDPC, BCH, those kind of mathematical ways. It can identify how many bits arrows are there in like 10, 12, 10, 24 chunk area. So this is a little different. I would say like parity chunk, it is more like to recover the chunk. The function is not for detecting errors. Okay, but it can do if your detection is about which chunk has some errors, then it is possible, but cannot be so precise to tell you what is where is the error. Okay. So I think we stop around multiple level cells. And also we talk about some like details about how to program read and erase. And I think in today's report, I will switch to Chinese to once again to talk about the read and program because there is a lot of questions about read and program last time during the break. So I think I can use Chinese to quickly go to how to do read and program. So that part will be Chinese and the rest of it will be English. Okay, so first thing we need to recall is the RAM. So the RAM system, it allows multiple hard disk drives to work together as a single system. If there is no management, we can say this is JBOD. JBOD, actually it is just a bounce of disk, so we call it JBOD. So with using JBOD, actually there is not too very intelligent or very smart mechanism inside. It's just about to put a lot of disks together to get super large capacity. And RAID 0, RAID 1, and RAID 5. So you will say RAID 0 is striking, and it is for performance. RAID 1 is mirror, it is for reliability. But they are like, they cannot do further trade-off. For example, for RAID 0, it can only get good performance, but it cannot trade to any reliability. RAID 1, on the other hand, it is for very good reliability, but it sacrifices a lot of other performance and also capacity. And RAID 5 is, you can think about it is a design between RAID 0 and RAID 1 because it involves things called parity. So parity is using some mathematical way to generate a dummy data chunks. This extra data chunks, it is not for storing data. It is for parity information for us to recover the data chunk. Well, if there is a crash in some disk. Okay, and in a disk, because actually for RAID 5, we can only allow a crash happens in one disk. So if you have two disk crashes, then I mean it is not possible to recover from RAID 5. Even you have a lot of disks that are using RAID 5 to control. Each time you can only recover one disk. If there are two disks, then it can't help. Okay, so this is for RAID 5. And then we talk about SSD. Actually, for most of the case, no matter SSD or USB drive or your like iPhone, Android phones memory, they're using NAND flash memory. So we talk about the details about like NAND flash memory, right? So this is NAND flash memory. Actually, NAND flash memory is like, there is sorry, let me use Chinese to quickly go to this part. Okay. 好，那这个地方基本上它就是一个 B 型半导体，然后上面接一个复杂层，然后复杂层跟 P 半导体中间会有一个介电池， 介电池它是一个可以被导通的，可以被导通的物体。那如果在没有被导通的状况的时候，它就是绝缘的状态。OK，所以基本上我们在做 program 跟 erase 的意思，其实就是 program 就是把 P 型半导体激活后，它上面会有电子，然后电子会被比较强的磁场吸引，所以它是有机会可以去跨过这个介电子的。那它需要足够能量，那这是 program 要做的事情。那在 bit 一的时候，其实就代表是它在复杂层里面是几乎没有电池的，那它可能是因为被 erase 或者它可能没有被 program 这样子。OK，那怎么去做 program 呢？基本上 program 功就是给一个足够强的电压值的20度，它就会产生强的电场。那这个电压会激活 P 型半导体上面会有电子出现。OK，那这边电子就叫游离电子。那游离电子因为它上面有强的磁场，所以它会被这20伏特拉进去这个复合应键。那这个20伏特其实在现实世界它不会是20伏特，它会根据不同 SSD 的规格，它会有一个自己的伏特数这样子。所以其实这只是个示意而已。这边的说 XML 只是示意，只是让大家有感觉它是高的比较大的词，比较小的词。OK，然后在读的时候要怎么读呢？读的时候基本上跟 program 是在同一个地方给电压，只是它给的是一个相对小，而且是小很多电压。哎，那基本上读的概念就是在这条 console 的 endpoint 上面，就是这个 P 半导体上面有没有办法有电流通过这样子。OK，那目前假设它复杂层里面就有一电子，假设我们给一个读的电压是2伏特的话，那 P 型半导体会激活非常少量的电池。OK，那这么少量的电子基本上它会被吸附到跟 source 跟 endpoint 上面，但因为电流是流动的电子，所以如果当电池的数目不够多的时候，它是没办法构成电流的。所以基于这个原因，这个2伏特只要控制得当，就只要够小，基本上是可以创造出真的是没有电流的状态。那没有电流的话，我们就会说，它就是零或一这样子。OK，那另外一个 example 就是如果那个复杂层里面没有游离电池的状况，就代表 P 型半导体是没有被激活过的。所以基本上，如果你给个2伏特的话，它会激发出比左边的情况更多的电子。就你们可以想象，P 型半导体的电子其实它是有点像是有一个某一个差不多的数目在的。那你给越多的电压，它就会有越多颗被激发出来。但是因为它总数是固定的，所以如果像右边这个状况的话，它之前没有被高电压激发过，所以如果你有2伏特的话，它会激发出比左边这个曾经被激发过的平半导体来讲，会再多一点点电池。那这个一点点电子基本上就会让它刚刚好可以构成电流，可以从这个 N source 到 N drain，然后就可以被接收到这样子。所以这个是读跟写，基本上都是针对 control gate 上面这个word line 去做给电压的动作。OK，那 erase 基本上它的意思就是要怎么把电子从播音给把它拔出来。所以 erase 这边的话，基本上就是在 P 型半导体这边给一个强的电压，那这边是20伏特。那给了之后，基本上它就会因为这个电子受到强的外力，所以它就被拉出来这样子，所以它就有机会透过接力的方式把它导走这样。那这样 P 半导体，不好意思，在活音层里面就没有复杂层里面就没有电池了。OK，所以基本上，状态的改变其实是看波音 gate 里面到底是可以讲的是电子多还是电子少。那 program 的意思其实就是把电子把它塞到复杂层，erase 就是把电子把它移出复杂层这样子。好，那这边给了2个例子来跟大家说，如果因为刚才那个只有一个 cell 嘛，这边一个 cell 就一个 bit 而已，但实际上你们看到的状况应该会是一个网格状的状况，因为它是一个就是它应该来讲会长这样子。那一个横的，我们叫它一个 wall line，一个 wall line 其实是一个 pad，一个 pad 是4KB 这样。那不同 SAD 其实不同的配赛，它有可能16KB 这样。好，那我们这边的电压值这边你可以看到有高有低，这边有一个很关键点，是因为我们就算用同一个电压给 P 半导体施加这个 同样的电压产生同样的电场，它不会有同样颗数的电子进到复杂层，因为我们制程是有 variation 会有变异性的，所以给同样电压的结果就会导致进到复杂层的电子数会不同。所以可以看到说这边有3.8、3.9、4.8，其实这边会有差异性存在这样子。好，那我们现在假设要把 pass through 去把它去做 program，那我们可以 to 这边假设是没有被 program 做过的，所以就是都是在一的状态。好，那是一个一是类比嘛，一是数位状态嘛，那我们实际上它里面应该要是这样子，它应该一个类比是1.9、1.9、1.9、1.9，代表里面基本上是几乎是没有电子的状态。好，那如果我们要把它去做 program 成1:1.0的话，也就是把这两个去做给电子的动作，那我们一样就是从control gap 这边给20伏特，啊，其他都上5伏特这样子。那给20伏特之后呢，这边后面两个就会变成电子就会从P 型半导体被拉到复杂层里面去。好，但为什么前两个不会呢？因为前两个它用了一个抑制电压在 bin line 上面。抑制电压的意思就是说，我们在就是这个是 bin line，这边我们先给一个额外的5伏特的电压，那20伏特的作用还是一样的，就是你有足够多的游离电子被激发出来了，可是它们跨不过这个介电池。原因是因为我们横向还有一个干扰的5伏特的电压，所以他们会因为被干扰，所以就会直接被拉出这个接地这样子。OK，所以基本上里面就不会有电子进去。所以这个抑制电压的功能，就是因为你这边4KB 的话，你可以想象成，如果一个只是一个 bit 的话，那它就是有4096 byte 这么多个nameplate 的 cell，所以每个就是要接一个抑制电压。如果你不想让它被破分的话，OK。那最后来讲一下 read 到底要怎么去 read。那一样 read 会给2.5伏特跟在你要读的人上面。OK。那这边值得注意一下，为什么其他人都是给5伏特的这个地方？原因是因为其他人需要是一个导通的状况。好，因为我们说这个 read 其实看最后面底部有没有收到电流。那如果我直接给5伏特的话，如果我们回到这个例子的话，直接给5伏特，2伏特跟5伏特的话，就代表是它一定可以激发出游离电子，因为它有足够强的足够高的电压、足够强的电场，它是会有足够的邮电能被激发，所以它一定会有电流产生。不管它这边有没有电子，它这边一定会有电流产生，这是5伏特的作用。所以5伏特意思其就是它会比读的电压再稍微高一点。那也是一样，反正这个基本上就是 SAT 厂他们会去做一个评测，知道说到底是2伏特还是5伏特还是多少伏特这样。好，那这边的话一样，如果我们是给2.5伏特的话，因为后面两个它刚才被 program 过了嘛，所以它的复杂层里面是有电子的。那你这边给2.5伏特的话，在它的 P 型半导体是无法激发出有足够数量的电子产生电流。那这边没有电流的话，它的电流就只会到这边停下来了。对，就像这样子，它电流就过不去了。对，好，那这样的话，基本上如果我们稍微量一下的话，就会知道说，这边的电流值就是全部加在一起的。那这边的电流呢，就只有后半段的这两个加在一起。OK，那这边的电流基本上他就知道说，那就是全部导通的状况，所以这边是1。那这边的话，因为中间有截断了嘛，所以代表它是有部分导通，所以就可以判断出它是0这样子。OK，这就是怎么去读。OK。All right, so that is about, I think it is a little bit difficult to understand in English, so I try to translate to Chinese, but I mean, it is very similar to the English version. Okay, so let's work on to multiple level cells. Okay, multiple level cells, it is talking about if it is possibility to let one number cell to represent more than 1 bit. Okay. Actually, now like it is possible to use one cell to represent, I think it's 5 bits, if I remember correctly, like Phison and I think like some company in China, they are trying to push this capacity. Okay, but I think the concept is very similar. But I mean, the technical part is super different, but we will not go into the technical parts. I'll just give you some concept about what is the challenge and why it is so difficult to move from 1 bit to 1 bit and to 1 bit. Okay, so for the 2-bit scenario, what we are going to expect is this floating can represent 2 bits. So which means there are 4 possible status, 1, 1, 1, 0, 0, 1, and 0, 0, right? So 1 means no electron, and then you can think about 1/3, 2/3, and 4 electrons. You can represent different stats. And if there is a scenario as, sorry, let's change here. If there is like 3 bits, so 3 bits means there are, we need 9 different stats, right? So 9, which means no cell, so no electrons or 4 electrons, and between it, you can think about it is like 1n, 2n, like 3n, like this. Okay, and then this you can map to like 110 as maybe you only have very few electrons, and 000 means like you have a lot of electrons. Okay, so this is the concept about the multi-level cells. Okay, so before talking about what is the difficult for multi-level cells for the program, let me first introduce the arrows for the SSD. This is very important for the SSD design. Okay. So there are various types of arrows. Today we will only talk about, I think, 1 or like 2 types. So the first is about what is arrow. So conceptually, SS arrow means cells contain an unexpected number of electrons. So its voltage value shifts, which means you use the same read voltage value, let's say 2 volt. You cannot read out the status that you expect it should be. Okay, so you can think about the arrow. It is more like you expect now there are like enough amount of electrons inside the Bohr cap. But actually, because there is some error happen, so the electrons they flee the S cap on the Bohr gap. So the number of electrons will not be the same. And it is very easy to think about if like if you are using SLC. Actually, it has super strong capability to deal with this error because there's only 2 stats. I mean, with electrons or there is no electron. So SLC cell is not really afraid of SSD error because a few electrons different, it doesn't really matter. But come to think about if you now have 2 bits or even you have, for example, 5 bits MLC cell, then the error matters a lot because you are going to differentiate across like 4 or even like 32 different status. So in this case, you have like 10 or even you don't have 10 electrons in a certain cell, it matters a lot. It is hard to decide what is the correct status. Okay. I think there is a various type of arrows here. So we first talk about one arrow. It is called retention arrows. The definition is a cell cannot permanently retain electrons. So electrons escape over time. So what does it mean? It means even you put your SSD there, you don't do any read and write. So one day the data will get error. The reason is, let me show you the reason first. Okay, the reason is actually would they be very, very frequent to fast error is how thick, what is the thickness of the dielectric layer? Because if the electrons can escape, which means your dielectric layer is too thin, so it cannot hold, it cannot make sure the electrons can stay in the cooling gas stably. Okay, and then this dielectric layer, actually this is a chemistry. So you say like you put it like 2 years, 3 years, or even more years, this dielectric layer will become thinner and thinner, right? I mean, there are compound materials inside, they will become volatile. So after this, they will become thinner. And not only this kind of stuff, but also like in what temperature and in what moisture, and also like how many times you do the program and erase. They will all hurt. They will all make the dielectric becomes thinner. So when the dielectric becomes too thin to hold the electrons, then there is an error. Okay, and actually the error will not be like all or nothing. What do I mean all or nothing is it is not like, oh, there is 100 electron inside, and if my dielectric is too thin, so 100 of them will get off. It probably is not like this. It is more like your dielectric is getting thinner and thinner day by day. And then after one day, maybe there is a super high probability for any of the electrons inside get clear. Then the error bits will start to climb. So by nature, actually the electron will not really like it's just about all or nothing. It will be like it will gradually clear. Okay, and what we don't want to see is this expectation. We don't know when it will start to flee. So we need some strategy, and this is called ECC and why it is. Okay, here. So let me go back. Okay, and this figure is going to tell you how serious the retention error is. So the x-axis there is the PE cycle. PE cycle means program and erase cycle. So program and erase cycle, which means how many times we probably program the whole SSD and then we erase it. Okay, so when you program the whole SSD and you erase the SSD, then the PE cycle will count 1. So usually PE cycle usually is for the whole SSD, not for only one patch. Okay, so this is the case. But I mean, in some very like special case, PE cycle can be also used in one patch if the wheel leveling doesn't do a good job. And the part of the wheeling I'll talk about later. So let's come back later to talk about PE cycle. And now we can just think about PE cycle, which means like how often you use the SSD. Okay. So 10 to the Q to 10 to the 5, which means 10 to the 5 means you use it very often. So you program it a lot of time. Okay. And those different colors of lines, which means how like in what durations the SSD will pass the retention errors. Okay. And the brown line here, which means 1 day retention errors. Okay, and then here are 3 day, 3 week, 3 month, 1 year, and 3 year. Okay, so 3 year retention errors, which means we put there 3 years and how much of error it is. So when there's more like the duration, if you in larger durations, you will see the errors will become more serious because you can think about like you put there 3 years and you check it, so probably the error will become higher than like 1 day. Okay. And if you look at this figure, if now the PE cycles now is like 10 to the 3 around thousands times to use an SSD. So you can see like oh sorry, I forgot to introduce the y-axis. The y-axis is called the bit error rate. So bit error rate means like how much error there is in a certain region. So like 10 to the minus 6, which means 1 error amount a million of, you can think about a million of cells like this. So 10 to the minus 2 means for there's 1 error for every like 100 of cells. And 10 to the 0, which means every cell they get an error. So this is the error rate. So higher error rate means your SSD is going to fail or like it's going to crash in very nearby. Okay. So lower bit error rate, like here, means your SSD is still in a very healthy status. Okay, so you can see actually the more you use the SSD, actually no matter which lines, they rise their error rate. And then if you like 3 years, you check every 3 years, then this error rate will get also higher, like the red line. Okay. So this is also the reason people say SSD is not super safe compared with the hard disk drive. This is because if you are using the SSD and you just put there, you don't do anything, it's like for 3 years, you can see like here, you put it for 3 years. Actually, there is still like 1 arrow amount million of bits. Okay, so million of bits is not a very hard, because million of bits just means like 1 megabyte usually. So each 1 megabyte there is an arrow. You can think about like this. And then if you have more, if you use it more, then this 3-year retentions will give you a higher error rate. So there's more errors there. Okay. So compared with hard disk drive, actually there is no this software. You don't use it for 2 years, 3 years, or even 5 years. The error will, I mean, the error rate will still be super low. Okay. Super low means here's 10 to the minus n, right? When people say the error rate is super low, it is usually lower than 10 to the minus 12. Okay, and in some cases, people will say 10 to the minus 16. So which means the error is nearly will not happen. Okay. When we dive into to see about like, so what would be the error pattern looks like? Then this this pie chart show you like actually there is 2 different source. One is from 0 becomes 0 1, and one is from 0 1 to 1 0. Okay, so what is the reason why like there is 2 different like patterns they were facing the highest error? So this is the reason we say this one is 0 0, this one is 0 1 1 0 and 1 1. So 0 0 means there are a lot of electrons inside the Bohr gas, and 0 1 is, which means it is 3 over 4, right? So the error is like this, from 0 0 to 0 1. So actually the error usually happens because when there are electrons, they will flee, they will escape from the Bohr gas. So the more the electrons you have, actually there will more electrons they will get escaped. So actually you can see 0 0 to 0 1 and 0 1 to 1 0. But there are very few reasons like the arrow will go for reverse directions, which means there are very few arrow that will become 0 1 to 0 0. Okay, so this is how retention errors happens in this SSD stuff. So I think maybe you will be quite curious about, is there any possibility the error will become in reverse directions, which means, is there any error will let one like network cells to change the status from 0 1 to 0 0? Yes, it is possible, but this is not called retention error. Sometimes there is a thing called read disturbance, or like disturbance error. So disturbance, you can think about like because we will do the sorry, let me show you. Okay, because actually when we do the programming, right, will give us very high voltage value to one patch. Okay, so because this one is super high voltage value, so probably the electricity field will also affect the neighbor. Okay, and this is called disturbance. Okay, even we use a 5 volt to protect them, but it is not enough. I mean, if this 20 volt is strong enough, then there are some probability like the electrons will become excited for different word line, and then you will get extra electrons. So it is possible to get to a higher voltage value. Okay, so this is called a disturbance. The same thing for read. Because when we are doing the read, actually it happens. Okay, so this is the reason I say there is some probability, but this is called disturbance, not the retention errors. Okay. So I'll just show you actually the error is because your dielectric is cheating to hold the electron. So when there are some electrons, they can escape from the dielectric layer, then which means there is an error. Okay. So I think there is another thing as so how to judge, how to know there is an error, because like when you are using the SD, like if there's no one tell you, hey, actually there is an error, then you don't know there is an error happens, right? So there are 2 ways to let the SSD know there got an error. One is an implicit way. So as we say, because the dielectric will get thinner if we use more frequent. So P cycle is one implicit way to know if there is an error. I mean, by heuristic, which means like we can say maybe when your SSD goes to like 1,000 of PE cycles, then probably there are some errors. So according to the heuristic, it makes sense. Okay, but it is not super precise. Okay, because we cannot know, so where is the error? I mean, it's in which bits, like this. So there is another way is like using the error correcting code, ECC, and they will return us a bit error rate. Okay, but because we don't have that much of time, so I will just show you there's usually in SSD now, people are using the LDPC coding. Okay, and thanks to the time people are using PCH. So you can think about there's using a mathematical way to calculate like how much of error it is. They will first do the calculation once you do the programming. So they can know, okay, so what is the pattern now? And it is a little bit like the parity check. Okay, so if you are interested in, you can take a look about LDPC and PCH. Okay, let's keep moving on. And the thing is actually, error is not only like measures for the reliability or like you cannot read the true data. And also means you will hurt the performance. The reason is if there are errors, then your SSD will try to deal with the errors, right? It will recover from error, they need to detect the errors, so your SSD should do extra work. So when SSD do extra work, which means it needs to sacrifice its performance. Because actually the thumb rule for SSD is to protect the users from passing any error. So error actually is more important than the performance in some cases. Okay, but the thing is the electrons do not escape in a uniform way. And due to a lot of reasons, there are cell variations, there are different number of writes. So here, when we do the programming, you can think about the y-axis now as number of cells. So when you get an SSD, then you can say, hey, there is 10 of millions or like billion of cells now. So you can do the testing, like you can give the same voltage amount, so voltage value, let's say 20 volt, and then you can do the programming. Okay, when you do the programming, you will see actually because of the cell variation, different cells have slightly different probability. Sorry, have this slightly different property. So actually, this resource will become a distribution, will become a probability. Okay, so which means like if we are going to use the same like 20 volt to do the programming, actually, like if let's say like 1,000 of electrons is the correct answer that we are expecting, then there's only like maybe 60 or 70% of the cells they can really receive like 1,000 of cells in the polling gap. And some of it maybe you can get more, but some of it can only get fewer electrons if we just provide this distribution. Okay. And how to read our data? We say we use 2 volt, right? But in the MLC systems, we should use 2 times. Sorry, if this is a 2-bit MLC, then we should use 2 times to read out. First, we need to first read from the middle, which says we will have 2 different reference voltage. Okay, in one bit SLC, we only need 1 voltage value, which says 2 volt. But now in the MLC, usually we need like 2 different kind of reference voltage. Okay. So the thing is, actually, after the retention loss, your distribution will look like this, right? Because if you still remember, we say, sorry. Here. If you still remember, we said the error will be like, if there's more electrons inside the cell, then more electrons will get off. So it will become more serious for higher probability for the 00 to 01 and 01 to 10 is two different status. Okay, so due to this reasons, which means 00 and 01, actually they will become looser than 10 and 11. Okay, and when this distribution becomes looser, then actually when you are going to use a standard voltage value to read our data, then you will get an error. Let's say, because if you use a standard voltage value, let's say 2 volt. So for some cases, we should read out some current value, right? But because too much of the electrons can fill the S gap, so actually you use a standard voltage value, you cannot get the correct answer. Okay, then the SSD will do the miss decision. Okay, so how to deal with this issue? Actually, we can use the things called retry. Retry is actually like if you use 2 volt to read out, then you will see, hey, actually there is a very high error rate. So you know this voltage value is not an appropriate one now. You should change the voltage value for reading the data. So there comes a retry. We try to shift the reference voltage to successfully read out the data. As we know, in most cases, the error is the electron will get S gap. So actually we can we can move the voltage value to the left-hand side, right? So we can decrease the voltage value. So this is the first retry. We get another voltage reference. Now we still, after applying the new voltage, we still see, hey, actually this is a high bit error rate because there is still a lot of error inside. So then we will keep moving the reference voltage to the left-hand side. So when one day we try, actually the second time we use the second reference voltage, then we say, hey, this bit error rate is low enough. Okay, maybe your question will be, how to decide it is low enough or not? It depends on the capability of the ECC. So when you are using different ECC coding, they will say, actually, I can correct like hundred of errors among like thousands of bits. So this is error correcting capability. So for those ECC coding for higher capability, which means they can correct more bits or more errors back. Okay. So this is it low or high bit error rate? It depends on what kind of ECC you are using. Okay, so when this voltage value applied and you get a bit error rate, and this bit error rate can be handled by your ECC, and let's say the bit error rate is okay, it's low enough, because your ECC coding can help you solve it. Okay. So here comes a real case. Like this is the numbers from a paper published, I think, in 2021 ASPLOS. So the x-axis is the number of retry steps. So you can think about this as n and n minus 1 and minus 2. And the lines and the dotted lines means how many n, like n here is 21 and n is 16 for a green line. Okay, so 16 means it retries 16 times, 21 means it retries 21 times. So you can see actually the y-axis is number of row bit errors per kilobyte. So when for per kilobyte, actually, if before reaching this ECC capability, then you can see actually for a minus, a minus 3, I think for a minus 3 for the blue line or like a minus 2, then actually we still get extra high error, right? There's like 500 amount 1 kilobyte of data. Okay, so the ECC still cannot recover. So only when the error drops below the ECC capability, we can start to do the retry. So this is the reason we need to retry a lot of time. We always slightly move the reference voltage to the left-hand side until the ECC engine says, okay, I can handle this bit error rate. Okay. Okay, so coming back, why we say it hurts the performance? The reason is if each time we do a retry, we need to do an ECC. to check about if this is possible to do the recovery, then it spends extra time. Okay, because the reference changes, which means we still need to read our data. Okay, without reading our data, we don't know how many error it is. So you change the reference voltage and you read it. So in this example, you can see for the blue one, the second patch for blue one, actually it tried for 21 times, which means it read 21 times. Okay, so this is the penalty. Okay, and this is just going to tell you like different retention, the x-axis is retention, and different PE cycle. There are 3 different scenarios. There is 0 PE cycles, 1,000 and 2,000 PE cycle scenario, and they all start from retention angle from retention edge from 0 to 12 bounds. Okay, so the number of retries they grows a lot when the PE cycles jumps to 1K. Like you can see when the PE cycle is 0, there is around 54.4% of the patches they need to do the retry when you use the SSD for 6 months. Okay, and then now if you use a lot of SSD and now the PE cycle climbs to 1K, which means 1,000 times PE cycles, then you just put there and you don't use for 3 months. Your SSD still need to do the retry, and the percentage is very close to like 100%. It just depends on how many times we are going to do retry. For some cells, for some cache, maybe you only need to do 6 or 7 times retry. But for some cells, you need to do like 15 times. Okay, so this is the probability to show you retry happens very frequently in SSD. Okay. Okay, so let's come back to a question as how to do the program for MLC. So for SSD, you all are very familiar. Just apply a large enough of voltage and then the delocalized electrons can jump into the dielectric layer. Okay, fundamentally it is correct, but for MLC, how to do this kind of stuff? Why not just give a very specific voltage value, which we say 20 volt, right? Maybe you have a fine grain control, you give it like 15 volt, right? Then you can get a correct voltage number. Like I think some people were thinking about why not just use this. Actually, it is not possible because the thing is it depends on how big, what is the thickness for each dielectric layer. And you can think about when you pick up a voltage value, like it is 20 volt or this is a 15 volt, it needs to apply to all the nameplate cells in the SSD. And usually in the SSD, there are million or even hundred of millions of nameplate cells there. So you cannot really know what is the status for each nameplate cells dielectric layer. Okay, so if you only use one voltage number, then probably you will not success, and you will see this kind of distribution. Okay, so what will be the better way is we program several times. Okay, each time we only give some, each time we only incrementally increase the voltage number. We slightly push the voltage value to do the programming. Okay, so actually we use a thing called incremental step post programming, ISTP. What is ISTP? We say like incremental step. So each time the SSD controller will apply, this P is called program, V is called validate, and the y-axis is the voltage value. So at the very beginning, actually, we give the small voltage value, right? And then we start to incrementally increase the voltage value. Okay. The thing is, each time we also need to do the verify. So verify is also called a read. So when we are going to do the program, actually it is not only doing the program. We need to split it to a lot of I would say like small pieces of program plus a lot of read. Because when we do the small pieces program, we need to make sure what is the distributions now. What is the distribution look like? are those cells reach a good electrons inside their Bohn gap. So we will do this kind of verify every time. So actually, this is the reason why MLC takes a lot of time we do the programming, because each time we do the program and we need to check it. Do the program, we need to check it. Okay. So this is the case. And it starts from a low voltage and it grows to a high enough voltage. So in this case, you can think about like here there are 1, 2, 3, 4, 5, 6. I think there are six different cycles, right? So the more cycles there are, I mean, the more fine grain you can tolerate, and you can control the electrons more precise. On the other hand, if we only have very few cycles, let's say 2 cycles, and then you first use 10 volt and then you use a 20 volt, and probably you cannot reach a really good control. For the bad control, usually, which means your MLC cannot reach this kind of distribution. Probably like maybe this will be super large, this will be super large, and the last two will be super thin. Okay. So actually, there is a very important stuff is how many steps we're going to use, because the more cycles we are going to do the program, then the more time we need to wait. Okay. So, okay, longer programming time, which means we need lots of B and B program embedded to make sure we are now on the right track to do the programming. Okay, so I think let's take a 10 and come back later.
Yep, we have some presentation that's Friday in my group, and we wanted to know where do we find the link?
I think it's on the first slide which I've shared on.
Okay.
Yeah, there's a link.
Okay.
There, it's on WebEx link.
Okay, thank you very much.
Yeah.
就上次的课程里面有写到说这个 FNR 说，老师那时候是讲说，我把你的针头靠齐，
对
旁边的话它就可以，就算是因为旁边会浪费掉，所以旁边的话它可以读下来。但是这样的话，因为你写的时候不是整块都会被写，这样我读就是这样不就等于是说它还是被浪费，因为它还是在这边旁边也是写那样子这样，不是这样，
所以它不是，所以它的容量不会是2倍这样跳。就是看你这边留多宽，它就是它容量会有牺牲掉多少。
我的意思说，那这样的话，我把它往旁边移的，往旁边移，不就是要让它容量变大嘛？但是
对
我这边灰色跟这个绿色，这样不是会写一样？因为我的 right 就是这么大，这样它也没有省到，就是我的绿色在这，跟灰色是一样之内的。
哦，没有哦，你看它是主要是看绿色，因为你看光这条里面，它绿色可以读2次。那如果是原本的话，就是同样的粗度来讲，它只有办法读1次，所以读1次代表是它这个资料就是假设就是1份这样子，然后这样是这一区同样区里面可以读2份资料。
可是就是因为我症结点是我写的话，不是这整个宽度一起写的。
对啊。
那所以意思是说这整块不都是一样的资料？
对啊。
那我要一样资料2份，这样。
哦，可是你这边写的话，它会写出不同的资料，因为它磁场的干扰是在这边，甚至会到这个地方。所以你今天这一块， 假设你原本先写的格，对不对？
嗯，
那第二块是叠在它的上面的部分写的，所以只有这一部分的资料会被跟动到。对，因为这个磁场就会影响到这一部分资料，然后所以这部分资料还是之前你 program 的时候的那个资料。对，
了解了解了解。
对
那 OK，那还有刚刚上课，因为上课刚刚有说就是有没有有点乱，就是我要读好几次来确保说我是不是读到就是不同的电压。那要读好几次，那他怎么知道他现在读的是对的？
他每读一次，他就会用 ECC 去检查一次
用
，ECC 去检查一次。
检查说现在是不是对？
对，它其实也不是对或错这么简单，它是有多少的错误在里面。因为如果看到这个地方的话，其实它最后可以接受的，就是它已经这第16次了，然后它终于可以接受的点，其实是它的 ECC 可以正确解回来的那个值。所以它如果今天假设每1000个bits 里面，它是 K byte 的，好像就是每8000个 bits 里面，它有100个错误以下，再帮它解回来。那以上的就代表它是解不回来的，只要解不回来就要重读。
所以是说我可能读某一次，然后解不回来，我再读再。
没错，它就一直读到可以解回来为止。
那为什么他不要一开始就用比较大的电压去读呢？就是
你说为什么一开始不用比较大的电压？因为它这个点，如果你用比较大的电压去读的话，你很有可能会就是读到隔壁的人。
你说因为如果它分布不是这样，我可能会
对啊，
假设分布是原本正常的，我可能会压到旁边去。
因为这个是基本上它应该是对每一个 page 它都要去做这个修改。对，所以它其实这只是一个 example 跟大家说，你看这是一个 bit 的状况，可是对于整个 page 来讲，我都是用同一个电压去读，所以如果你今天一次把它调很大的话，那很有可能是根本区分不出这个00跟00的状况。
了解，
没错。
对，老师那个问问题我还要找。
就是如果现在这边问的话，就写下你问什么问题这样子，然后是哪一天的学号，然后就寄到助教信箱去。
就我直接写，我不用在 Webex 上面。
不用，因为这边有录音，所以对，我们会知道。
OK，谢谢。
然后这是 HDD 哦，
这是 HDD 吗？我看起来，
因为不是说像这种
看起来是啊，但是要看它什么，因为它 HDD 跟 HD 多2.5 英尺的话，但是它应该再更大一点。
如果会震动很吵的话，这样就是 HDD 哦，因为
震动很吵的话，
就是它可能会有点就是震动。
通常硬碟通常不会有这么小的，通常我不知道你是多大，但是通常
就是差不多这样。
那我觉得比较像 SSD 的感觉，几率比较大，不确定，感觉应该你插在电脑上知道吧？
插在电脑上知道。
不，我就写这 SSD 的硬碟。
那我想问一下，就是上次不是说 HDD 的话，你要更改前面的资料的话，你要把后面的就是也读出来，然后到另一个地方，然后再把它。
说 HDD 吗？
对
，HDD 不用啊，那就直接改。但是 SMR 才要。
对啊 ，SMR。
对，通常这种不是 SMR，
可是
通常要很大还是 SMR。因为这种就是你不在乎容量嘛，所以你买一个比较小的。因为 HDD 的容量就取决于它的磁盘有多大。所以你要在乎容量的话，你就会用很大的磁盘，所以它就是那种3.5那种，就是比你的手掌还要大的。对。
那假如说 SMR 这样要读出来，那它是就是一个装饰，因为它会有另外一个就是缓冲的地方哦，就是让它就是写东西进去，然后再先移出来，然后再
理论上不会，就是它在 SMR 里面就会有类似的区域。这个区域呢，取决于你 SMR 要花多少成本，它可以是 DRAM， 也可以是一般的 HDD 的磁区也可以。对啊，
所以假如说这一颗是用 SMR 的话，那所以它就是会在底面，
它会有例如留10%是正常的 HDD， 让你可以各种更改都可以的。对，它不会真的整颗都是 SMR， 因为这样它会做不了更改。然后如果你用 DRAM 的话就很贵嘛，因为你还把 DRAM 插进去，这样。
所以它就是会结合就是 memory 这样。
它会结合，然后通常它都是会预留可能10%是传统的 HDD， 就是 CMR 这样子，然后有90%就成的是 SMR， 然后它还有额外的 DRAM， 那它额外 DRAM 是拿来存，就是暂存那个资料写进来的时候，它要 buffer 存的。
对。 那我想问一下，就是因为我们 USB 是 NAND flash 嘛，
USB 是 NAND flash 对。
那会不会就是因为 USB 比较长，就是所以那个坏掉，就是比如说它如
对啊
果突然它格式化，所以就是因为它是 NAND 的，
啊，
那 HDD 就比较不会这样。
也不会这样。那 HDD 不会知道 USB，对啊，
哦，
因为 HDD 它就是需要那么大容量，所以它基本上就无法，它再怎么样都是这么大。
好，这样子。
对。
No. I don't think they still say it. I mean. Well, I don't think so. But they sold very purple things. What else do you play? It's crazy. It was socially I didn't I just always like this night I was like in bed. 2 days I still for on difference. I need the time like this because I don't want to go next time. Check. I really start and everyone. Like but I was like, okay,
Okay, so let's come back. I think there is an interesting question in the chat box. Can we perform dynamic switching between MLC modes to optimize endurance since QoC has marginally lower PE cycle? Technically, it is possible, but practically it depends because actually we need to control how many voltage it is. So actually you can think about there are different like this kind of configuration table in current SSD. So previously there is some SSD vendors that are doing SLC plus MLC, this kind of stuff. So actually it is possible. Okay, but usually like MLC and QoC, usually it doesn't see too much of effectiveness. I mean, if it is QoC, then probably people would like do it with like SLC and QoC. So SLC can mainly focus on the endurance, and QoC is for like a higher capacity. Yeah, but I mean, it is doable for the switching. Okay, but if you are saying about if it is possible to reconfigure some cells to QoC to like SLC, I would say like it is usually this is a research topic, and probably for the industry perspective, they're only make sure, for example, the first 10% it is SLC and the last 20% it is QOC. They were not dynamically switched in rules. Okay. So let us, okay. All right. Let's come to a more coarse granularity about SSD. Before this slide, focus on is here, nameplate chips. On the chips, there are die, there are channel, there are die, and then there are block. So there are like patch, and then we say chip sales. So we focus this sales management and then how to do a read, how to do a program before this slide. And after this slide, we are going to talk about a more broader concept. What does SSD really work? Okay, and one more thing, actually, like if you are a little bit familiar with SSD, actually for most cases, like nameplate chips, I would say like the vendor for nameplate chip usually you would think about as like Samsung, SK Hynix, this kind of company. And now like Phison, usually they have a few amount of nameplate chips, but not super large, super huge. And then because I think you guys will be familiar with the company just like Silicon Motion and Bison. These two, usually Silicon Motion and Bison, they work intensively in the controller design, not on the chips design. Okay, so I'm just wanting to let you know there are a lot of different rules inside SSD. Different companies, they contribute different like also there is someone like I think you will be also one question about why like when you are going to buy SSD or like USB, usually you will not see like Phison or like Silicon Motion. This is because the SSD usually they only use Phison and Silicon Motion chips for the controller. So the rest of it is still not like from Phison or Silicon Motion. Okay, so this is the things. But if you like find something like Samsung, because Samsung have their nameplate chips and they have their controller, and then they can assemble it together by themselves. So Samsung has their own SSD. So like this. Okay, so today we talk about the flash transition layer, and flash transition layer it is inside the SSD, which says on the SSD there is a microcontroller, and a microcontroller will run two different functions. One is called flash transition layer, and the other is called memory technology device (MTD). And both of FTO plus MTD, you can think about they are firmware. So firmware in Chinese is 韧体, and then it is different from the driver. So driver is called 驱动. So device driver is part of the operating system, which means device driver is not inside SSD. Device driver is outside SSD. Like CPU will run the device driver. Okay. MPD is quite, I would say like, MPD is quite, maybe simple is not a good word, but in this course, I would say it doesn't have, we don't talk too much of MPD in the rest of the course, because the rule for MPD is going to interact with the nameplate chips. So, which means like, when the MPD receives the request, it needs to package and you need to reform the request to fit the stack of the nameplate chip. So it needs to know what is the physical address and then how to read, how to program. So those kind of stuff, they are handled by MPD. But we will not talk too much of MPD actually. We talk more about FTO. So what is FTO and what does it for? So mainly it is for, because we say for the nameplate chips, it can only do the outplace update, right? For the SSD, because the erase operation has you need to erase more patches, and then the read and write granularity is still in a patch granularity. So this kind of granularity mismatch between the erase and rewrite operations, which led to this kind of out of place update, which means when we are going to do the update means we still need to reset the bit value and then we do the write. And when we talk about reset, which means erase. So we cannot directly erase a patch. So we need to read out the patch, modify the patch, and then write to the other place. So this is called outplace update. Okay. And there is also another thing is sequential write constraint. So I think this is a very similar idea. Sequential write constraint means like when we are doing the write, it should be sequential because we cannot do the update in place. It should be sequential. Okay. So when we are doing this kind of sequential write, when we are going to follow a sequential write constraint and to handle a complex update, a very key thing is about the address remapping. Okay, and I will show you why address remapping is super important later. Oh, here comes. So here is the name flash block, and I have different amount of patches inside. So for example, if this is a patch, and the data content is like this bit string. So actually, we will get two different kind of address. One is called, one is called LBA 500, the other is called PBA 800. LBA is a logical block address. PBA is called a physical block address. So physical block address is like a physical address. So this is a stepping number for the nameplate cells. Actually, from the SSD perspective, it always see like PBA 800 is here. Okay. Logical block address is not for SSD actually. LBA logical block address is for the user, is for the application. So application actually you can only see the LBA. So you can think about the device driver will send out to say, hey, can I read or write LBA 500, the data stored in this location? And then the SSD, the FPO layer will try to do the address translation. Okay, so why it is needed to do this kind of stuff? Okay, the thing is, when we're doing a remodified write, we are going to read out the old path and then to modify in the DRAM and then to the code to the new lattice data, and we write that to the SSD with different path, right? But from the perspective of the user, actually, you don't really want to know what happens inside SSD, right? For you just want to know, you try to update the data, you try to update your word, you try to update your PowerPoint, you try to update anything, and then you don't want to know like, hey, actually, your data moved from one place to another place, so you need to do some extra work to handle this kind of stuff, right? So from the user perspective, your word file is still stored in LBA 500. The difference is now this file, after the updating, it is now PBA 1201. Okay, so this mapping, this update mapping, there's only maintained inside the SSD controller. So outside CPU doesn't know what happens inside the SSD. Even outside CPU, it doesn't know there is a PBA inside the controller. Okay, so from the outside perspective, from the user, from the application perspective, it only sends the request using this LBA stuff, the LBA 500. And then this is what the very important stuff. Due to this design, when you plug in the SSD to the systems, and no matter what kind of read, write, erase comment you send to the SSD, you don't really need to worry about, hey, SSD is different from hard disk drive. SSD should follow the sequential write, should follow the outplace update. No one needs to care this stuff because the controller inside SSD will help you fix all those kind of stuff according to this kind of address remapping stuff. Okay, so address remapping inside the SSD is super important. Okay, and this remapping, there is no relation between the operating system. There is totally different two systems. Operating system is upper, outside the SSD. Okay, so patch table, those kind of stuff. And this one is totally different. Even they both code patch table, because actually when the FPO controller is going to maintain this relationship, like where is now the LBA 500 points to, we still need a patch table. Okay, and this patch table is different from the OS patch table. Okay. Okay, so after doing the remodified write, the next step is to do the invalidation. Because this is a stale, this is an old patch, and they're outdated, so just mark it as invalid. But the thing is, if there are too many patches in a block becomes invalid, then we can think about we should do the garbage collection, right? Because if there are too many invalid data, which means it is our capacity. The more invalid data it is, fewer capacity we can use, fewer capacity SSD can offer to store the data. So if there's too much, then we need to do the garbage collection. Okay. Okay. So when we're going to do the garbage collection, actually garbage collection is going to, first, we need to move the live data. We need to move those valid patches to some other place before we do the erase. So garbage collection also needs to, it also needs to work with the address translation layer. It needs to know like which patch is valid, and then we need to move the patch from which block to which the destination block. And then after that, each time we are going to contact the nameplate chips, we need to run the MTD. Okay, so no matter you are going to reprogram erase, we should need the help from MTD to do this kind of operation. Okay, so I think you can see there is a thing called DRAM, right? DRAM inside SSD, usually this is a very huge resource. And then there is a translation table. So translation table is going to maintain a relation between LB and PB. So you can also think about this is a patch table. And the size actually it is quite huge. Usually like 1 terabyte of the SSD. Now you need like 1 gigabyte of the translation table at least. So actually this consumes a lot of like memory. Okay. There is another component called wear leveler. Wear leveler is because I think you can see there's two words. Wear means like we are going to write the data to the nameplate cells, and the dielectric layers will be worn out. So this is called wear. So the dielectric layer becomes thinner and thinner, and this is called wear out. So level, which means we are going to evenly distribute this phenomenon to all the cells. The thing is, we say if we frequently, intensively to only write to one cell, then the dielectric layer will become too thin to hold the data, and the cell will become error prone, right? So there is a possible way is we should distribute all the write access to all the cells. So in this case, in this case, the SSD can handle more writes. Okay, so this is how we're leveling can help, and we will talk about details later. So first of all, address translator. So the limitation is nameplate cells should follow the erase before write property inside each block, so data should be outdated out of place. Okay. So physical layout of flash memory. You can see this is a block, and usually they are depends. For some SSD, it can be 512, for some which can be 128. So it depends on different SSD vendor, different SSD spec. So in this example, we'll just use 112. And then for each SSD patch, it can be 4 kilobyte, or it can be 16 kilobyte or 8 kilobyte. It just depends. So follow the stack, and then if this is a 4 kilobyte, usually there is still a very tiny area called housekeeping area. So this 64 byte, it is possible to use to store some ECC coding. So if it is hard to figure out what it is, you can think about just like a parity, bits. But it is different idea. I'm just going to let you easy to understand. So formally, we say we put our ECC corrected information in this 64 byte. So it is possible for us to check if there is some like errors inside this 4 kilobyte area. Okay, so for block, it is a basic erase operation unit. For patch, it is for basic rewrite operation unit. And then there is spare area. So spare area is for housekeeping information. Okay. So the goal is to hosts do not need to handle this limitation. So when we are using the SSD, we users or even applications or even some others, they don't really care about this is SSD or this is hard disk drive, right? What we are going to do is just plug into the systems and it can give us a very fast experience and it is enough. We don't want to handle those tedious stuff. So tedious stuff is handled by the controller inside SSD, as we just mentioned. So host only interact with the virtual address. So this is a host, application, driver, OS, they're in a host CPU. Okay, so extend the virtual address, or like we call it logical block address, it will be to the controller. And then this SSD maintains its physical to physical mapping table in the DRAM area. So the mapping table is stored inside the SSD. So the controller will first check about, hey, if we have this OPA, what is the corresponding physical address? So the controller will check the DRAM and the address packing. The controller will get a PBA. So using the PBA, actually, like we can do this kind of output of the stuff. Okay. Basically, there are two different ways to do this, to maintain this patch table. The one is called patch table. The other is called block table. So patch table, it is about to translate the address in the patch granularity. And the challenge is very obvious because it will, in this case, it will make your translation address tables very huge. Okay, and how huge it is? Usually it is around like 100,000 of SSD size. Okay, so let's take a look at this example of how patch table works. So if this is our patch table, then for the patch table, like it will show us about the block and path it is. So the first block, the 0 patch, the fourth block, the 5th path. Okay, and given there is a LBN, so like this is the index, so from 0, 1, 2, 3, 4, 5, 6, like this. So if we are going to read out LBN 3, okay, then we are going to know what is the physical address, right? Because LBN is just for user, but we don't really know the physical, the true address on the SSD then flash chips. Okay, so we say LBN 3 now, we can get block 0 and patch 2, right? So now it's like this, block 0 and patch 2. So here is the true location for the data. Okay, and usually in the housekeeping area, we will say, hey, this is LBN 3. So it is easier for the controller to do the reverse mapping. So this is also one thing for the housekeeping area. Okay. So now another example is if we are going to write to LBN 3. So because we cannot do in-place update, so we cannot do right here. What we are going to do is we are going to we are going to get a new path from other blocks. And because this is a new path, so we can write data inside. But what kind of data should be right? Then it depends on what you are going to write to. Okay, after writing the data, this is new data. And then in this case, we can get our new physical address, which means block 1 and patch number 255. So after getting this new physical address, controller will try to update the patch table. So the new patch table will look like this. This is block 1 and then patch 255. Okay, so because this patch table is stored in a DRAM, so we can directly update this block. Okay. Okay, so after doing this update, then this will be marked as invalid. Okay, so there's invalid here. Okay. So SSD will run the copy collection to remove this invalid data later. Okay, so this is the case. Okay, so let's do some, I would say like simple mathematical stuff. So now if we have a 1 terabyte SSD and there are 256 4KB patches in a block, so which means this is 1 megabyte. Okay, so we have 1 megabyte of block, which means 1 terabyte divided by 1 megabyte is 1 million. So there are 1 million blocks in SSD. We are going to do the calculation. How much DRAM capacity do we need to store the patch table? Okay, so to locate a patch, usually we need 20 bits to find a block. 20 bits means we can locate 2 to the 20 blocks. So 2 to the 20 blocks means million, right? 1024 times 1024. So actually it is around million, more than a million of blocks. So we actually need 20 bits. And then we need add this to find a hash. Why it is add? Because inside one block there are 256 hashes. So we need add bits. 2 to the add is 256. So probably we need 20 add bits for this kind of mapping stuff. Okay, and how many pages are there? So you can just do some division. 1 terabyte divided by 4 kilobytes, so there are 256 million of pages. And then total size is 256 million times 20 add bits. And then because usually we use byte, so we divide it by add. So now you can get add 96 megabyte. Okay, so this is like for 4 kilobyte page size, and if the block size is 256, and you have 1 terabyte SSD, and this is the DRAM consumption we should have for maintaining the page table header table. Actually, it is quite hard because, you need to sacrifice 1 terabyte of DRAM for doing this kind of page table stuff. Okay, so there is another way, like people are thinking about, is how to minimize this DRAM consumption. You can use a thing called block level address translation. It translates the address in a block unitary. Okay, so the good thing is you can minimize the table size. Okay, but the bad thing is it incurs the write overhead, and also it decreases the low block utilization. So also let's go to see an example. So now we have the same thing, virtual block address from 1 to 6. And then inside this each entry, what we are going to maintain is block number. So because this is a block level, so we don't have path information. Okay, we only have block information. So now if we are going to write to LBA20 add, okay, so LBA20 add, what is LBA20 add? LBA20 add, we will do some mathematics. So because if there is like 120 pages too hard to draw, so I just give you a tiny example. Now let's assume each block only has 6 pages. 1, 2, 3, 4, 5, 6. So each block 6 pages. Okay. So if the system receives like LBA20N, they will first do some transformation. The system will first divide 20N by 6. So to find where is the block, because this is a block label, so actually we only can maintain the information related to the block. So we can say, oh, actually the LBA20N now, actually it will be mapped to block like 4, the VBA4 now. Okay, and this is the virtual block address. Okay, and this virtual block address actually it can be mapped to a physical block address. Okay, so if the physical block address now is 24, then probably the data is stored in 24. So you have another question. I mean, there are 6 pages in this block. So where does LBA20N really points to? Okay, so we need to do another calculation, as the page number will be like 20 modulation by 6. Okay, because there are 6 pages. And then if we get 4, which means 0, 1, 2, 3, 4. So, 4. So this is the 4th page here. So now we can know how actually the physical block is on block 24 and the page number is page 4. So this is where LBA20 really points to. Okay. Okay. So after finding where is the data stored in LBA20 then our next is we are going to do a write. So write, which means we need to do update, but we cannot directly do the update here, right? Because we will erase all the things, so it is expensive. So what we are going to do is to find a full free block. So let's say block 62. Block 62, it is a new block, so there is nothing in the blocks is added. Okay, so we are going to write the data to it, right? So in the block label, this is quite tricky because we don't have hash information. So what we can do is we directly write LBA20 the new data to the same locations. So this is the 4th page in 62. Okay, and after that, because we can only maintain the block label information, So we should move all the used patch in block 24 to block 62. Okay, and I think you know what happened because block 24 will not be used in the future. This will become invalid. We directly change to the new block. In this case, we only need to change the block number to from 26 to 62. Okay, so you can see like LBA 28 is 62, right? Then there's some other like LBA like 22. It will be also mapped to the same block. So in this case, we should help to move other valid data to a new block. Otherwise, if there comes another LBA numbers which maps to the same VBA number 4, you cannot get the right data. Okay. Okay. Then because it is using a block label, so actually like it really don't need too much overhead because you can think about each block can share the same DRAM entry. So it saves a lot of things. Like for 128 of the patches in the block, they only share one entry. So the size will directly divide by 128 directly. So for the FTO and block label, like this is type label, this is block label, the RAM consumption is a super huge gap here. Page label, like this is 2 gigabyte, and if you are using the block label, you only need 11 megabyte. Okay. But I think it's the right time because actually if we are going to do the right, actually for the block label, you can move a lot of stuff. So this also, the overhead will be 128, like more serious than page label. You need 128 times of the write times. Okay. So this is the comparison between the patch and block label. Okay. I think, let me stop here because I think we only have 15 minutes left. I'll first hand over to the TA to go through our first assignment and then, yeah, we can call it a day. Okay. So, one moment.
Okay, yeah. Sorry.
Hi, I'm one of the TA for this course, and I'm going to give you an overview for this assignment. And in this homework, you need to conduct an experiment on your own device. And any storage device is acceptable, provided you can just justify your result. And please ensure that your config in the FIO setting is specified for each question. And here's the outline of the assignment. Let's get started. So the first is to ask, what is FIO? And FIO is a tool for benchmarking and testing the storage device and the file system. For example, it helps us determine how fast a device performs under a specific workload, such as measuring the execution read bandwidth of SSD or hard disk device. So how to use FIO? First, you need to download it. And next, we need to prepare an FIO file. For example, you prepare a Q0 FIO, and then we run the command below. So this command is to run FIO using your configuration setting in FIO file, and the output will redirect into the output file, and you can check the result after the FIO program is finished. So after you execute this command, it will begin benchmarking the settings described in your FIO file, as I said before. And note that you may need to have sudo permission to run this command. So what is a FIO file? So the FIO file is something like the picture I shown below. And the FIO file is a job file, is a plain text configuration file used by the FIO tool to define exactly how a storage benchmark should run. And you will need to adjust different FIO settings for each question in your assignment. For example, you can set the RW to read or run read to benchmark different settings, and more details you can be found on the website. And there is a caution here. You can assign the file name parameter to either a specific file path, for example, it's a file, or a raw block device. If you are testing a writing behavior, writing directly to a raw disk device is destructive. It will bypass the file system and partition table, which can permanently override the existing data. So you need to be aware that if you are doing some tests on writing behavior, you need to create a pre-allocated test file on a mounted file system, not just test on a raw block device. And here are some submissions. You may need to notice that you will need to answer the question in a PDF report, and please attach your FIO setting code outside the report additionally. And all your files should be organized in the following format, and you need to zip them into a zip file and name as this term. And the deadline will be 1 month later. Here are the grading policy. There are 4 category score you can get, and you will get no point when you don't follow the submission rule I mentioned before, or you cheating, or you late submit. So if you have any question of this assignment, you can reach out to TA by the discussion forum on B3. Any question? Okay, thank you.
So if there's no question, let's.
Okay. It's okay to use Chinese to write your PDF report.
Oh, if there's no question, let's call it a day. Thank you, guys.现在吗？天啊，我怎么会？而且我资源证不见啦。
我们先走之前，我有看，但我没有看到很清楚。
然后掉到路边了，要重办一张哦。
可以问那个公平。
要问一下。
For the homework?
For homework，大家看。
Oh, I was just, it's more of a recommendation question, like,
Yeah.
I have, well, do you think it would work fine in terminology?
Maybe.
I'm not sure. If it does, do you think, because it's storage system, do you think?
I think it's okay to run on Apple, depending on our
Direct.
yeah. And be aware for when you test the right behavior.
Be careful.
Yeah. You can ask ChatGPT
What to be careful for.
what this line mean. It's like if you don't really understand what this line is mean, you can
Just make sure I'm careful about.
like when you test the right behavior, you need to yeah.
If I'm still okay to.
Yeah, it's okay to ask the question in a forum.
Okay.
I'll answer you.
Thank you.
Guys.
建议用 Linux，然后可以自己就开个序。
可以，如果你考得出来的。 我没有试过，但你试过。
不然你是用 Windows 吗？
我有说你一点。
所以我们车档用自己写。
特市长对。
我在这里，好像是特例，但是你们说那个 OS 的速度会比它对，
对，
因为是因为它要编译的速度强。
没有，我指的是你跑任何 OS 的服务，它会比 DM 快。因为你要想，第一个它其实只是个硬体，所以你做一个动作，它只是你会对，所以 OS 是一段扣。一跑扣的话，就是代表除非你跑什么一个有双线，那当然快。那如果你 OS 就是什么几百到几千个有双线，那一个100个有双线，这种的话，一个礼拜大概就跑1耐嘛，这样大，所以至少100耐怎么才去？对，所以其实你出去了 OS 的，我们基本上是已经可以，只控制基本上的。
哦，所以不是编译的问题，
不是，
对对，刚刚也是编译问题，我想说，那这样我只不要谈到 OS 来讲，
哦，没有，它是指 OS 在跑到 runtime 的时候，它的速度会比你较慢。哦，对。
问的就是那个 BTH 的话是比较broken gate 那个电子比较多的话，它的那个 BTH 就会
对，
或者好那bit error rate 是什么意思？
第二个意思就是说，那么1000个 bit，那它有100个出错，那它 bit error 就是1000个 bit。就 bit error 很低。那让别人看你是要解码或解读啊，比如说解读4KB 的话，那它的 error 就会几千到几万，我就出现就非常或者这到底是不严重？通常比较轻的话，就代表是什么10个6以下，它就比较可以被接受。哦，对。
那这个谁person mistake
就是我们在说它的电子行业状况，它其实很难用一个分布来去做描述，因为你要想它这个 SD 里面是有上千万个 cell，每个 cell 它都是不同的 cell，所以它的每个 cell 它的薄度是不同的，那个界面的薄度，所以今天它的逃离的难度是不太一样的。有些 cell 它可能非常那个电子的好，有些 cell 可能它可能马上就界面的。所以它就要很准到它才会跑出来，
所以才会用这个 distributed 这个，
就是它应该说理论是它测出来就是它是这个 distribution，应该大概是你都给一样的电压，然后你测完之后你会发现你的那个每一个 state 它所需要的电压是不一样，因为你这边的电压是你没有办法变动，
所以这个reference voltage 的意思是
reference voltage 是假设你在用很多的话，那就不是。对，那基本上如果它是就是 retention 之后的话，那两个可能就会有一部分的数据会读出来的，因为它有一部分的电子在很平面里，所以代表它的那个电子的数目已经不多了。对，所以有2部分理论是读出来到底是
所以要就是这个 view reference 要是正常，应该是要在这个 distribution
中间，对，它才可以比较好的去区分是在左边右边的，对不对？
哦，
因为它那个电压是要去区分是有电子跟没电子状态。
那为什么这边是一层哇左边？
因为它的 error 是基本上。有一个，这边这个，反正这边其实应该会有张图在告诉我们 error 长相。那它 error 其实都是会往左边移的，因为你在对，这个，因为你满的时候是最容易掉电的，因为电子最多，所以它只会往这边移。它只会是电子跑掉，它不会是电子进，就是多出来的。
所以它这个
所以它这边一个或者这边一个，
对，
它只会往因为它不会是掉一堆电子。
所以这个 reference 对，
你说 reference 存在意义吗？是，就是你要读的时候呢，你这边是2个都会读，那你之所以可以用2个 A 读，是因为2个都可以明确的区分是左边右边之白。而今天如果2个都没办法明确区分的话，就是如果它的电很差，它这样子，那2个就有可能会读错。它不会说什么你什么
所有都读不出来，它可能是个10%的位置，10%的错误这样。
可是假如两题都在这里的话，不是都读不到？
哦，没有，这个是两伏特的意思，其实是你这边给两伏特嘛，然后根据刚才那个意思是，你给两伏特之后，你要看它激发出觉得很P 型漫会激发出电子，然后这边左边的部分呢，因为它是投轨过的，所以它是有更多的电子在左边电里面，所以这边不会有电子产生，这边都会有电子产生。所以今天如果它这个有人移跨路线过来的，代表它里面电子是不多的，那 P 型半可以激发出来，它就很有可能会形成一个电流。它原本这边这条线左边，但右边是都没有电流。
哦，
对啊，
因为越来越就是越来越入手。
对，越来越入手，它代表它的电子会流回 P 那里面去。
哦，所以就是就是区分这样的。
对，有没有电流不知道。
那这边的图其实我是看，我只知道好像就是
这边的意思其实说，那这边其实这边意思其实说，因为它给固电的定压的时候，其实每个 cell 它可以打出的电流是要不同的，所以在 program 的时候，它也是用这种分型的那个。
哦，
那你今天去 program 一个 page 的时候，它是4000多个 cell，所以它没办法说你要什么里面是有72颗电子，你就直接打到那个电压处。如果直接这样打的话，一定会有人很多颗，一定会有人冲出来。所以基本上我们就是一步一步慢慢打。我们这边比较小心，你可以再加进去。所以这个意思就是电压一步一步加进去。那我每次加一点小电压，就是做一个 merge，去确认说它到底是在，就这个把它确认到底它多少电压，电子
是
渐进式。
假如我现在要从就是program 到0，然后我就要一直打电子到1 gate，然后
那我不能一次给很大个，
一次打一点，这个会不会行？然后
我每打一次就打一
还
次。
是验证一次，然后直到了那个
对，
到
那我他觉得 OK 的，他一定
到 OK 的话是基本上是漏还是会带来
OK 的话我们看，他会分成看看什么。loose 的意思就是说有没有产生，因为你放了很久啊，然后它变异了。
那这个 attribution 之类的方式，基本上就是有一个 map 去map table 去对应，
对，
就是
对，或者是
那这个 table 是存在
第二边，
一认，我觉得这个 translation
对，
好，谢谢。
好，谢啦。